In this video, we take a look at problems from section 3.3. Specifically, we're going to look at a saddle point problem. Okay. The differential equation we're considering in this problem is dy dt is equal to b, or so let's call it a times y, and where the matrix A that defines this system of differential equations is 8, negative 11, 6, negative 9. Okay. What we know at this point is we need to find the eigenvalues and eigenvectors, because these will eigenvectors because this will lead us to what are called your straight line solutions. And once you have your straight line solutions, you can use the linearity principle to find any other solution. Okay, straight line solutions were the subject for section 3.2. So we'll do an example real quick. Recall that the eigenvalues, we need to define the characteristic equation, okay, which was obtained by looking at the eigenvalue and eigenvector equation AV equals lambda V, subtracting lambda V from both sides, turning that into AV minus lambda times the identity matrix times a vector V equal to 0, factoring out the vector V, and then we're looking for V not equal to 0 solutions, which means that we need the matrix A minus lambda I times V to have a non-zero solution. So you need the determinant of this matrix A minus lambda I to be equal to 0. Okay? So we can go through that now. On this other side of the screen here, I've got, just to show those that are trying to do the computer, you can define in this Mathematica, for example, a matrix A. You can define a matrix called the identity, and you can show that the matrix A looks like what we were saying, 8, negative 11, 6, negative 9. So this is how you type in a matrix, and you can convert it to its matrix form. And so it looks like we've got the right system. Okay. What you need to do is take A minus lambda times the identity matrix. Okay. And you can see that that did something, and if you turn it into its matrix form, you can see that we got A minus 1 times lambda, negative 9 minus lambda, and then the identity, since it was 1, 0, didn't put lambdas on this off diagonal. So there's A minus lambda I. Okay, we need to compute what's called the characteristic equation. The characteristic equation is obtained by taking the determinant of A minus lambda times the identity. So your characteristic equation comes out to be lambda squared plus lambda squared plus lambda minus 6. Okay, and we want that equal to 0, and now you need to solve this equation. Okay, so you can use the quadratic formula or factoring, or you can ask a computer to solve it. Solve that equation equal to 0. And now we are seeing that there come out to be two solutions. Lambda is negative 3 and lambda is equal to 2. These are your eigenvalues. Okay. You can go on and compute the eigenvectors. The eigenvectors of these eigenvalues. How are you going to do that? You're going to solve AV equals lambda V for the two different choices of lambda. So now you need to solve A times V equals negative 3V. And we're looking for V not equal to 0. And we know that there will be a solution for only the values lambda is -3 and lambda is 2. Okay. So if you continue on and solve the system of equations, AV equals -3V, okay, where V is some vector xy, V is x times y. Set up a system of equations for that. Okay. A is 8, -11, 6, -9 times the vector xy. Set that equal to -3x, 3y. Okay. Continue on and multiply this matrix out. You'll get 8x minus 11y. That's the first entry of the vector. And then you'll get 6x minus 9y. And that's supposed to equal -3x, -3y. Okay. So this is specifically for the eigenvalue -3. Okay, solve this system of equations. You'll get, adding 3x to both sides of the top equation here, you'll get 11x minus 11y is equal to 0, and you'll get 9x, you'll get on the bottom equation here, you'll get 6x minus 6y is equal to 0. Okay. Taking this equation here, for example, tells you that x has to equal y. Okay. If x is equal to y, then you get 11x minus 11y, x from the top equation, right, which says that 0 times x is equal to 0, which is true for any x. So if x can be anything and x has to equal y, then your eigenvector v is x could be anything and x had to equal y. So y had to equal x, and therefore your eigenvector was 1, 1. Okay? So for an eigenvalue of -3, your eigenvector, one of your eigenvectors, the simplest one, comes out to be 1, 1, which tells you that one of your straight line solutions is e to the -3t multiplied by 1, 1, which means that e to the -3t, e to the -3 is your y1 of t, one of your straight line solutions. Okay? So the trick is to find these eigenvectors, okay, to find the eigenvector here. You can do that on the computer by taking the eigenvalues that you found, okay, and you can use a linear algebra technique, row reduce the matrix A minus, and take one of the eigenvalues, 3 times the identity, okay, row reduce that matrix, okay, and when you do that, convert that to its matrix form, what you find here at the page below, okay, what you find here is that when you row reduce, if you're using linear algebra techniques, that your system row reduces to 1, 0, 1, -1, 0, 0, which is a fancy way of saying 1, -1, 0, 0 times xy, okay, which led to the equations x minus y and 0 times y. Okay. And both of those will be equal to 0, so it says that y can be equal to anything, and since x minus y is equal to 0, that says x has to equal y, and therefore you get your eigenvector y anything and x is equal to y. Again, you're led to 1, 1 as your eigenvector. Okay? So that's for those that want to do the steps to use the computer. The other eigenvalue was 2, So if you ask the computer to row reduce a minus 2 times the identity, right, what you'll find here is that for the lambda equal 2 eigenvalue, you row reduce, the system is row reduced to this, okay, which is a fancy way of saying, you know, you're looking at a minus lambda I times v equal to 0, which is a fancy way of saying 1 negative 11 sixths 0 0 being multiplied by xy had to equal 0 0, which tells you that 0 times y is 0, 1 times x minus 11 sixths y has to equal to 0, which tells you that y can be anything, and x has to be 11 sixths of that anything. So this tells you for the eigenvalue lambda 2, its associated eigenvector is y can be anything and x can be 11 sixths times y, which if you factor out the y, you get 11 sixths with a 1. Now this is rather an inconvenient eigenvector because of the fraction here, but remember any multiple of an eigenvector is also an eigenvector. Any constant k times an eigenvector is an eigenvector. So this means that I can, for example, multiply 6 times my eigenvector will also be an eigenvector to give you 11 sixths. This is a nicer eigenvector. It doesn't have fractions. Okay. So what we've found there is what we have discovered is what the demos, our Mathematica demos show us. Okay, let me show you the code that we have here to double check your work. Okay. You put in the matrix into the differential equations demo, the matrix and some initial condition. Here's your matrix A. Here is your initial condition vector. And the first step was to compute the eigensystem. You can see here that the first eigenvalue was -3 and the eigenvector was 1, 1. And for the eigenvalue of 2, we got 11 6, which is what we showed from before. Okay. The next step is to take your straight line solutions. There was the first one we found for the eigenvalue of -3. And here's your second straight line solution, y2. Okay. And you can use the linearity principle to solve your initial value problem, which we'll do now to show how we work towards this solution. And then we will discuss what's going on with the source sink and saddle behavior. Okay, so let's continue on to the next step. Okay, now that you know your straight line solutions, and we have two straight line solutions, y1 and y2. Okay, y1 came out to be e to the -3t, e to the -3t. That was for the eigenvalue -3. The second straight line solution was 11, e to the 2t, 6e to the 2t. That was for both of these are the form e to the lambda 1 times the first eigenvector, e to the lambda 2 times the second eigenvector. These are your two straight line solutions. Okay? Now we know that if we have an initial condition vector, okay, our initial condition vector is -1, 1, which means that our initial x for the differential equation is -1 and our initial y is 1. And we know that these were the initial conditions for the differential equation that we're solving. The differential equation is 8x minus 11y, and dy dt is 6x minus 9y. And this is essentially just a long way of saying that d capital Y dt was the matrix A times y. Okay, so now we have these initial conditions, and we want to find our solution y of t, and we know by the linearity principle that it's going to be some constant times our y1 straight line solution plus some other constant times our y2 solution. Okay. And we know that what we want capital Y of t to happen is that when you put in 0, okay, you'll get y1 evaluated at 0 and your second straight line solution evaluated at 0. Okay. But that just becomes k1 times your first eigenvector plus k2 times your second eigenvector, and that's supposed to be equal to your initial condition vector, right? Which leads to the system k1 plus k2, k1 plus 11k2 has to equal -1, and 1k1 plus 6k2 has to equal 1. So now you need to solve a system of equations, right? And then you will find that k1 comes out to be 17 over 5, and k2 will come out to be -2 over 5. Okay. So we know here now that our solution that goes through the initial condition in question is 17 over 5 times y1 minus 2 over 5 times y2 of t. And you can expand that out, right, to be, work that out to be whatever x of t and y of t comes out to be. You can expand. Okay. What you will get there, okay, is what we are seeing right there. When you expand, this is the x of t will be the top entry, and y of t is this bottom entry here. Okay, so we've essentially found x and y as functions of t. Okay, so you could plot x as a function of t, and you can plot y as a function of t. Right, and you can see here that probably as from the x solution, we know that x, for example, comes out to be, now you start to analyze the solution that you found. Right? And you have these constants that are in play, 22 over 5 and 17 over 5. But it's interesting to note about what happens as t goes to infinity. As t goes to infinity, you're seeing that this term is getting closer and closer to 0 because of your negative exponential. But it is because there's a positive number here for the other straight line solution, this one will cause, as t goes to infinity, will make x get bigger and bigger going to infinity. So whatever happens for this, for the x, in the x plot, plotting this function, we know that at time 0 we're going to be at an x value, at time 0 you're going to be at an x value of 1. And then whatever happens as t goes to infinity, the solution is going to go up to infinity. Okay. And for y of t, your solution was 17 over 5 e to the -3t minus 12 over 5 e to the 2t. So as t goes to infinity here, our y value started at, x initial condition was -1. Sorry about that. The result is still the same in the long term, that you started at -1 and then the solution goes up to infinity. Y starts at 1, and you can see here that as t gets bigger, this term goes to 0, but this e to the 2t causes the solution to Oh, and in fact, actually, they're going to negative infinity because of the minus sign here. So the solutions will go down this way and down this way. Okay? So the question that's happening that we're really concerned about is these time plots are usually not the most functional ones to look at. What you're more interested in is the xy, the phase plane. Okay? And we know here that x, our initial condition, was -1 and y was 1. So here's your initial condition. Okay? And the question was, what happens to our solution? Okay? How does it behave in the long term? Now remember, we had two straight line solutions, one with an eigenvalue of 1, 1. Right? So there's one of your straight line solutions. And the other one went over 11 up 6. So you've got another straight line solution here. And if you notice the eigenvalues, one of them was positive for the y1 solution. Our eigenvalue was negative. So here's your y1 of t. The solutions were negative. The eigenvalues were negative, so that means that if you're on that solution, you're going to go in towards 0, 0. And the other eigenvalue was positive for y2, so we've got solutions going out this way. Okay. Now that's what happens if you're exactly on the initial condition somewhere along this line. Okay. What you can then do here is sketch these solutions, right? That if you're in the initial conditions in this area, you're going to be following this solution, but then you also have to follow the other one. Okay? And if your initial condition on this side, for example, you have to be following the y1, but then also following this one. And let's see. Yeah, and then there was a second. So this is a very rough sketch. We need to show a better sketch. But this is, if you know your straight line solutions, they will help you, guide you with sketching your solution. So some initial condition on this side should be going like this. Okay, so let's double check our phase plane. All right, for this problem. I may have, I think what we need to do here is draw this sketch again. I think I've got these vectors kind of drawn a little bit. I think I've got one vector being above when it should be below. So let me just draw a better plot here. Okay, so if you're going to get a good phase plane plot, right, x versus y, you need to get a good sketch of your straight line solution. So your straight line solutions was 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. 1, 1. There's your vector 1, 1. First eigenvector was 1, 1. And the second eigenvector was, what was it, 11, 6. So 11, 6 is trying to divide everything by 6. So remember, another associated eigenvector, also an eigenvector, is divide everything by 6. So 11 over 6, 1. 11 over 6 is a number bigger than 11 over 6 is bigger than 1. No, it's less than 1. Give me 1 second. Yeah, okay, so we're back. So clearly 11 over 6 is less than, let's just do this, 11 over 6. Turn it into a number. Okay, so it's bigger than 1. So if you go over that much and up 1, the second eigenvector is down here, v2 and v1. Okay. So, sorry, I had to think about that for a second. It's the easy math that'll get you. So now what you can see here is that we've got two straight line solutions, the v1 eigenvector solution, and then the pink one. I'm exaggerating these because they're rather close together. And here's v2, which leads to the y1 solution. The y2 of t, and the other line was y1. Okay. And we know the eigenvalues, right? We know the eigenvalues for the we know the eigenvalues were for y1. Yeah, so plus 3. Oh, it was a minus 3, so y1 is solutions are coming in this way along this initial condition. Okay. Initial condition coming in this way. If you're on this straight line, solution is going to go into 0, 0. Along the second solution, the eigenvalues were initial conditions will go away. This and eigenvalue solutions will go away from this equilibrium point 0, 0. Alright, so now we got the hang of it. Now we can draw what happens to initial conditions here. Initial condition in here will follow the one solution, but then it has to turn. Initial condition over here, like the one we had, has to follow these arrows, right, coming in, and then it keeps going down this way and then not crossing. So here was the solution y of t that we had, right? We can see that as t went to infinity, when we looked at the x went to negative infinity. And as t went to infinity, y also went to negative infinity. So here was our solution y of t. Here's the initial condition. As you follow it in time, both of these, the x and the y, will tend to negative infinity. So, sorry that took a second to work out the drawing of the eigenvalues and eigenvectors. The trick there is that they're so close together, so you do have to watch out a little bit. What we're seeing here, right, here's a really nice computer plot of what's going on. You can see your straight line solutions. Here's your y1, and then there's a y2. Notice that the arrows are coming in and in. This is your negative eigenvalue, straight line solution. Then there's another one, y1, going out with the arrows going into the equilibrium 0, 0. Okay? And you can see here by adjusting the initial conditions that, right, initial conditions between those two straight lines are going to come in and turn. Initial conditions outside of the straight line are going to, they're going to bend, turn and go down to negative infinity. And then here's another solution down here. Okay? Which is consistent with what we could see on our hand-drawn picture here, that initial conditions down here would follow the arrows up, but then they come into these other pink ones, which also forces them to keep going up. Okay, so yeah, very rough sketches going on here, but I think everything kind of comes into play. In the next video, we'll just do a quick summary of the different saddle, source, and sink behavior. What we're seeing in this problem is because you've got one of the eigenvalues turned out to be positive and negative, then what we're seeing here is that the equilibrium point 0, 0 is what's called a saddle point, which means that in the phase plane you're essentially getting solutions which have negative eigenvalues and positive eigenvalues, right? which means that solutions kind of have this kind of looking behavior, which is what we're seeing here in this problem. It's just that the straight line solutions are really close to each other, so the solutions are bent like this. Alright, that'll be a good start for a video.